my name is Jasmine, and today we'll talk about the tiny particles of quantum mechanics. So what if I told you that the smallest particles in our world act completely different when we're not looking? They can be here, 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 or here, maybe even here, all at the same time. Crazy, right? How can we explain the physics of these particles, knowing that they can be in many places at once?
Yes.
Well, that's exactly what a few physicists have accomplished. Erwin Schrödinger added the last piece of the puzzle, bringing to life our modern theory of quantum mechanics, which has helped shape our world as we know it. To help us understand quantum mechanics, let's first take a look at how classical physics works. You see, we can easily find the trajectory of this soccer ball if we're given an initial position and initial momentum at which it's being kicked. This can be done by using Newton's second law of motion, which states that the sum of all forces acting on an object is equal to the mass of that object multiplied by its acceleration. So let's say you kick a soccer ball, and we know the position it's being kicked from, which direction it's going, and the force at which the ball is being kicked. Then we can easily calculate where the ball will be at all points in time. And no matter how many times we run the experiment, as long as the initial conditions are the same, the ball will always travel the same trajectory and yield the same results. These are called deterministic results because they will always be the same, and no randomness will happen. The best way to explain this phenomenon is by analyzing the single and double slit experiment of both real-world objects and subatomic particles. Let's imagine we're kicking soccer balls again, but this time we want to shoot them on a wall with a slit in the middle. Behind that is another wall that we will use to show where each ball will hit. I'm going to try to kick them as straight as possible, but my aim isn't always the best. Ultimately, we will end up with a range of possibilities that look like this. So what if we conduct the same experiment, but this time we use photons instead of soccer balls? Well, as you might imagine, after a while we will end up with a similar range of possibilities. Makes sense, right? Let's now add another slit right next to the first one, and run both experiments again. What will happen? Well, if we try and kick soccer balls through both slits, some will hit the middle and bounce back, but others will make it through, and eventually we will end up with a distribution that looks like something we could have predicted. But what if we now try this experiment with photons? This is where things start to get a bit strange, and we witness each photon hitting the second wall in an unpredictable or random location. But they're not completely random. Eventually, we end up with a distribution that looks like this. What the goose? This makes absolutely no sense. This cannot be real. But it is, and we'll prove it together right here, right now. Here we have a shimmer photon firing out of this laser into the double slits that I made on the piece of aluminum foil, and out onto the wall where we can see the interference patterns they make. Here we can clearly see the interference pattern we were talking about. It worked. The middle is where the stream of photons are most intense. To the left and right, we can see the same distribution as mentioned in the second double slit experiment. That's crazy. The only way this interference pattern can be explained is by the superposition property of waves. But that would mean that the photons act both like a particle and a wave. How can a photon or any subatomic particle be described as both a particle and a wave? This still doesn't make any sense. And we have yet to find a concrete answer as to why this occurs, but we call this phenomenon wave-particle duality. This is what I meant when I said that particles can be at many places at once. They can be described as waves. So how does classical physics differ from quantum mechanics? And more importantly, what is quantum mechanics? Well, the goal of quantum physics is to mathematically describe the motion and interaction of subatomic particles such as photons and electrons. But unlike classical physics, where its results are deterministic, these results are probabilistic, meaning that if we run the same experiment with multiple particles such as photons, they won't always yield the same result. Instead, there are probabilities for what results they will give. Its discovery led Schrödinger to create an equation that describes the probability at which quantum particles and systems change over time. This formula is as important to the field of quantum mechanics as Newton's second law of motion is to classical physics. The construction of the quantum theory is the driving force toward the digital revolution. Without it, solid-state physics wouldn't have been developed, and transistors wouldn't exist, which means the computers as we know them would only be part of science fiction. Thus, I would have not been able to make this video for you guys to enjoy and learn from. Thanks for watching.